Okay, so everybody, welcome to the Flexcom 8.6 eSeminar. As you're all aware, Flexcom 8.6 was released just very recently, just 2 weeks ago, and I'm here today to give you a brief overview of the features which are contained in the latest release. My name is Angus Connolly, I'm Product Manager for Flexcom, and I'll just walk you through the new features now by way of presentation and also some software demo. I'll start by giving you a quick outline agenda. With Flexcom 8.6, we introduced a variety of new features into different categories. The first one is primarily user experience, that we've made the software faster, more responsive in terms of how you interact with it from a user perspective. We've introduced a 3D plotting feature, which is quite nice. So you can plot variables as a function in two-dimensional space. So for example, if you're doing a regular wave matrix, you can plot, say, maximum tension or moment as a function of both wave period and wave direction. It just gives you a nice overview of the engineering data. We've made some advances in terms of model building that is quicker and easier to build more complex models now with Flexcom 8.6 than it was in the previous version. We've added a very powerful facility called user solver variables in this version of Flexcom. This allows the user access to the internal solution variables which happen in Flexcom at runtime, while the simulation is progressing. So you can actually go in there and you can modify, say, the global force vector to apply an arbitrary load as a function of time, which also depends on the conditions in the model at that point in time. We've got a couple of examples that'll become clearer when we talk about it. Runtime performance is something we're always trying to improve on, trying to make Flexcom run faster, so you have less waiting time for simulations to complete. We've made some advances in the area of pipe-and-pipe modeling, a little bit more options for the user, and also advanced documentation, just much more clarity there, transparency of what the user is doing, what the program is doing while it's running. And then a couple of more minor features like a nonlinear damper element and some additional outputs. So I'll work my way through these points one by one, showing you some information on the slides, and then we'll have a look at the software as well. The first area I want to cover quickly is user experience. And just before I go any further, just on each of these slides you might see a blue information symbol up on the top right hand corner. I'll provide you with the slideshow afterwards in a PDF format. So if you click on that blue button, it will take you directly to an area of the online help where you can get more information about the stuff we've spoken about during the presentation. So hopefully it'll be useful later on as well to you. So that blue button is something that we'll look out for. In terms of user experience, Flexcom 8 is a very powerful program, and I spoke to quite a number of people over the past year to 18 months, and one of the comments that I heard quite a lot was that the keyword editor of Flexcom, although it's quite useful and gives you a lot of input prompts, it could be slow to respond, particularly for large keyword files which have got thousands of lines in them. So we made a few different changes in this version to make it much faster and better user experience. The first thing we did is we optimized the source code so that the program actually runs much faster now. A second related theme is that for keywords which tend to be quite bulky or contain a lot of information, we've actually allowed the user to sort of farm out that information into separate files. And we'll see both options here now as well. So I'm just going to briefly switch over to the Flexcom software. This is a very large keyword file. There's almost 6,000 lines of data. But you can see as I type, it's pretty responsive. No real noticeable time lag. There's a little time lag, but not a huge amount. I'm just typing in some kind of random numbers there. But if you try this with the previous version of Flexcom 8.4, the program would just lock up. For a keyword file with 6,000 lines of data, it just would be unworkable in the Flexcom editor itself. So rather than users reverting to text editors like TextPad or Notepad, Notepad++, I'd like to think that this version of Flexcom you can actually work within the software regardless of how big the keyword is. So the keyword file there is like almost 6,000 lines of data, but it's still reasonably responsive. as you type. So I think that's something you'll just get to grip as you use the software. But for now, you can just sort of take my word for it, and if you have any feedback, you can certainly give that to me as well in your own time. The other item I wanted to just note is, let's go to the online help here. I'll use this blue button myself. Bring up my Windows Explorer here. Scroll down. Okay, so all of these keywords here, like added mass, radiation damping, vessel data, REO data, QTS, they tend to be quite long because you have a lot of data at various wave periods, wave headings, etc., different frequencies. So for all of these keywords now, there's a file equals option. So if I just switch maybe to an example to show you. The uploading, floating, won't save that. There, so static. So if we look at the added mass, and radiation damping keywords, rather than having hundreds and hundreds of lines of data, you can just reference an external file using a file equals command, and that cuts down all the data that's in the keyword deck, which in turn makes the keyword file much smaller. So this one is, only a few hundred lines long, but even if it's a few thousand lines long, the software should be more responsive. Back to my presentation. Okay, so user experience, faster keyword editor, and also we have some keywords now which reference external files, which makes the keyword file, the main keyword file, much smaller, more compact. Does that make sense to everybody, or does anybody have any questions on that? Okay, I'll proceed on the basis that we're okay on that topic. As I said, we can have a Q&A session right at the end anyway with more detail. 3D plotting. This is a very, very nice, attractive feature in Flexcom 8.6. And it just gives you an advanced visualization of data. So rather than looking at text outputs or 2D graphs, which can be quite bland, now we have a color contour plot in three-dimensional space, which is really good for a visualization of where the concentrations and critical design parameters are versus the input parameters like wave period and wave direction. I'll just maybe show you this in more detail because it's very useful. We've added some new example projects. So if you go to the example projects and J, which is the specialized example section, there's a new one here called summary post-processing collation. I'll just open this. My laptop is a little slow to respond, but I'm still waiting for an upgrade. So this is a plot of effective tension, the maximum effective tension versus wave period and wave direction. The plot is fully interactive. You can zoom in and out. You can spin, rotate, whatever you want. You can get... I've just managed to do something there. That's the trouble with a live demo. I'll just go back to the default view, which is this one here. So if we look at how this is created, I'm using a parameterized keyword file where I've parameterized some input things like wave period and wave direction. I vary those, so wave periods from 5 up to 25 seconds and directions around the clock, and I use that keyword file to generate lots of other keyword files. So for example, 0 degrees, I've got all these nicely named files with correct inputs. So this all leads to the generation of a spreadsheet, which is the collation spreadsheet here. Let's open for you. Like I said, just bear with me because my laptop is not the quickest. Okay, so when you do any given analysis in Flexcom, what you can end up with is a summary output file, which I think you're all familiar with. It's a text-based file which looks at various parameters you want to look at in the model. So von Mises stress or bending moment or tension. It tells you what the minimum and maximum values attained in that simulation are. When you use the collation facility, you can actually gather all that data from a load case matrix into one single spreadsheet. And then at the end of that spreadsheet, it will tell you what is the worst combination of inputs. So let's say the maximum effective tension in this simulation occurs at a wave direction of 150 degrees in a period of 11 seconds. And it tells you what the simulation is, so you can find that. What we've added in this version is an additional capability, which I will go to here. What we had in the previous version was the ability to collate data into a spreadsheet. Now we've added a facility to plot data as well in a three-dimensional plot. And the only thing that you need to watch out for is your primary axis and secondary axis, and these are just parameters in the base file. So if I go to any file here and I go to the summary post-processing section, I just define parameters called period and direction under this collate plot axis keyword. That's a new keyword under summary post-processing, and it allows you to store key parameters for each simulation in a database for that simulation. Once you've stored them there, then you can go to the collation input file and reference them there again. So very straightforward. Once you start to use it, you'll see what the benefits of it are. That's tension, bending moment. You can retrieve anything you want as well. You can zoom in, you can turn on some tooltips. So if you turn on the tooltips, that will let you actually retrieve values from the screen as well. So you can see that's, say, 36 megapascals von Mises stress for a wave period of 22 in a direction of 120 degrees. I think it's a very nice, very useful feature, and I think once you start to use it and become familiar with it, it'll be something you'll really enjoy. Back to my slideshow. Again, bear in mind, if you click on that blue button at the top, you can get more information on how to actually create the plots and how to manipulate them. So if you don't remember everything I've just said on screen, you can actually go to the relevant section of the online help and actually get information as well. Does anybody have any comments or questions on the 3D plotting feature? No, it sounds okay. I'll just double check the sound quality here. Everybody seems to be okay. Zaki has a question. Do I need to call the guest? Yes, I'll just answer that. Okay, back to my slideshow. Model building is the next thing I just want to briefly speak about. Flexcom 8 introduced the lines feature, which made it very easy to model, mooring lines or risers using a couple of very quick keyword commands. Whereas before, in the older versions of Flexcom, you would have had to do nodes and elements. So the line command has automatic mesh generation, which is very useful. What we found with the lines command is it wasn't perfect for sections which kept repeating. So with it, say for a drilling riser, for example, you might have a lot of different riser joints separated by flanges or separated by buoyancy material, and the same type of section was modeled over and over and over again. And that required lots of different line subsections, each of which had to be defined explicitly with a unique name and so on. What we did in Flexcom 8.6 is we've introduced another input, which is called line section groups. So you can define a small section which you can then repeat and reference many times via the lines keyword. So for this floating hose model, which you can see on the right hand side of my screen, that took over 230 lines of data to build in 8.4. In Flexcom 8.6, it's only just over 30 lines. It's very concise. I'll just quickly switch back to Flexcom to give you a demo of it. This is in the floating hose example, which is number E3. Go to star line. I can just do the lines table here. Line section group. So for this floating hose model, which I could probably just throw open on screen. We can have a quick look at it. Switch off the node numbers. So I'll just zoom in here. So it's a floating hose model between two vessels, and it's basically each section has got a start, middle, and end. So you've got a bare section, then a buoyant section, then another bare section. So if I go back to Flexcom, I'm defining a section which is called, bare or hose start, and then I've got a buoyant section in the middle, and then an end section. And then when I go to the line command, which I'll maybe show that in the keyword. Again, so start, it's 3/4 of a meter of bare section, 10 meters of buoyant, and then another 3/4 of a meter of bare again. When I start to define the lines, the first one is just a connection at the end of the line. This is the first section with the actual part of the hose. So I'd have the line 01, that's just the name, but these are the start and end locations, and this is the mesh density. At this point, in the old version of Flexcom, you would have to define a different subsection for each part of the hose. Now you just have one subsection, but within that subsection you have repeated many times the line subcomponent called line section group, which you can repeat as many times as you need to. Usually the length of the subsection would be divided evenly into the total length to get an even number or an even multiple of subsections. But if that's not the case, then it just simply truncates the last section appropriately. But you'll figure that out pretty quickly yourself. So one new keyword just to be aware of, it's called line section groups. Very easy to use. Once you've defined a subsection there, you can then reference that within the lines command using this repeat option. So very easy to build up a complex model, which would have been quite tedious to do in the older version. Any questions there? Is everybody clear on that model building? I think much of this material is self-explanatory, and maybe we can just have the questions at the end. But the theme for this version 8.6 of Flexcom was to make the software much more usable and user-friendly, and to empower the user. And this is the overall theme which we're aspiring to. On that note, I'll move on to the user solver variables, which this is a very powerful feature, but it's intended really for advanced users of Flexcom, who really want to get more out of the software than is available as standard within the software package itself. So this is very much in line with the plug-in type of nature that you'd have with a generic package like Abacus or ANSYS, where you can write your own user subroutines, compile them, create a DLL, and then plug that into your main model. So it's a very similar theme here with Flexcom 8.6. With Flexcom 8.4, there were user subroutines there, so in theory you could define arbitrary loading on a model. The main limitation with the older version was that when you wrote your user subroutine, you needed to know exactly what the loading was as a function of time before you started the simulation. And that's not always possible, because sometimes the forces or the effects that you wish to achieve are dependent on the local conditions within the simulation at any given time. So what we did in this version of Flexcom was we provided a brand new template which is completely open-ended and powerful, and which gives the user access to all solution variables at that instance in time. So if we're looking at a node in the model, you'll have access to displacement, velocity, and acceleration terms for that node for the current time step and also for the previous time step. You'll also have access to internal restoring forces like tension, moment, shear as well. So you can really do anything you want with those variables. And you also then, crucially, you have access to the global matrices that Flexcom actually solves for. So you'd have the global right-hand side force vector, and even the stiffness and mass matrices on the left-hand side of the equations of motion. So it's very powerful, but you will need to have some programming knowledge or knowledge of finite element solution techniques and an ability to write Fortran code or C++ code or whatever it is to actually create the DLL. Probably best explained by an example, so I'll quickly change to an example. Again, it's a new example. It's under the section J, specialized example. There's a new section here called user solver variables. There's actually two subtopics here, follower force and a sphere contact. So I'll just the follower force is quite simple, so maybe we'll just quickly start with that. Throw that open on screen. Plan view. So the line is quite small there. I hope you can see that on screen. But basically, I have I'll just turn on the boundary conditions. So we have a fixed end and a free end. And at the free end, I'm applying a force. So the force initially is vertical, but as the element rotates about the fixed end, then the force remains perpendicular to the element. So it follows the line of action or the line of rotation of the element. That effect you wouldn't really be able to achieve with the standard version of Flexcom, because you'd only be able to set up the force in a particular direction. Or you could do a time history, but in that case you'd still need to know exactly how it behaves as a function of time. So a very simple example, but it illustrates the concepts. I'll just quickly show you the source code for that. Just the example itself. There's very little in terms of keywords. The only keyword that you need to look for here is a new keyword called user solver variables, and then it just references a file which is a DLL which you would have pre-compiled before you've done your Flexcom simulation. So this is the new template, user solver variables. As I said, you'll need some experience with either Fortran or some other programming language to get the most out of this, but it is quite simple. What we have at the top is just a subroutine call, which is just a header block which nominates a lot of variables, and then beneath that it tells you what the variable types are and explains what they mean. So it's all nicely labeled in terms of comments. It tells you what each variable is and what its significance is. So there are basic variables like the number of nodes and elements in the model. Then as you move down, there are solution variables like displacement, velocity, and acceleration at the current time step and at the previous time step. And then you've got all the element restoring forces like tension, shear, torque, all that. All this information is available to you. And then what the user does, as you do when you write your subroutine, is you can actually modify some of the solution variables in Flexcom, such as the force vector on the right hand side of the equations of motion, or indeed if you wish the mass and stiffness terms. But normally it will be the force vector you'll be applying to apply some loads. We don't need to go into too much detail. You can probably read the subroutines in detail yourself if you want to get a better knowledge of what's happening. But basically it loops through the elements there in the model, finds the element that it needs, sets up some transformation matrices which go from local to global, because in the Flexcom solution all the forces and the stiffness terms are assembled locally with respect to the element, then transformed into the global axis system before the solution happens. So you do the same thing when you write your own inputs in terms of user solver variables. So it just puts a load on perpendicular to the element, rotates it to global, and then adds that into the global force vector at the appropriate location. And then just one thing to be careful of there is as well, when you are actually changing the global variables, what you do is you add more information and more terms onto the variables that are already there. You don't replace them. You actually supplement the vectors and the matrices the Flexcom provides you with. You don't overwrite the data that's there. You add your new terms to it. That one is pretty simple. I just quickly look at a more complex one, which is called sphere contact. Just throw this one open on screen. Just zoom in a little bit. Turn off the water maybe. Turn off the boundary conditions. Okay, so I can just turn on the node numbers so you can see what's going on. So basically, we've created a spherical surface. The spherical surface there is just, or it's a semi-sphere, half a sphere, and that green surface you see is really just a picture which we created using the auxiliary panel. But the main thing is that we've created an analytical surface in space using an algorithm. And if I just hit the play button, I just drop an element on top of that circle and it just falls down to the seabed. So in Flexcom, the standard version of Flexcom, we don't yet have a spherical contact surface. We do have flat surfaces and cylindrical surfaces, but we don't have a full sphere. So we wrote an algorithm as a user plugin which models a spherical surface, and that's what we can quickly look at here. Again, in terms of inputs, the keyword file is very simple. It's just one new keyword which references a DLL. The crucial part is the definition of this DLL, which you would write yourself in a programming language. And I'll just quickly have a look at that. So the header block is all the same. That's just the various arguments and what the types are. Then it just loops over the number of nodes in the model. And then it starts to find the distance between each node and the center of the circle. And if that distance is less than the radius, then it designates that contact should be modeled. If not, it just ignores it and moves on to the next node. If the node is in contact with the sphere, it sets up a local normal vector, which points from the center of the sphere out to the node, and then it sets up a local stiffness term in that direction. So the direction of resistance will be perpendicular to the contact surface at the point of contact. Once it's got that set up in terms of a local stiffness vector, it rotates that into the global solution system. Then it just does one or two other things there relating to angles and using functions just to make sure the angle is between plus or minus 180 degrees. And then that's, as I said, it rotates the stiffness from local to global, and then it adds that into the global stiffness matrix at the correct location. And then right at the end, it adds on a right-hand side term as well, just to compensate for the fact that the stiffness term doesn't kick in until contact is made, because Flexcom solves for position in space as opposed to displacement from initial position. So when you add on a new stiffness term to model contact, you actually have to add on a restoring force term as well, just to cancel out the force being applied before contact is made. We don't need to get into too much details there. That's very very in depth and maybe beyond the scope of this introductory presentation. I'll switch back to the presentation again. If you need more information on it, you just press the blue button. It'll take you to the correct section of the help. If you need more help than that, beyond that, you can give me a call or you can contact the software support service. Does anybody have any questions, or are we okay to proceed? Everybody is staying fairly quiet, so I presume I can just proceed to the end, and then we can take questions, and I can stop the actual recording, and we can take questions. Runtime performance. This is just self-explanatory, really. Flexcom is quite an old program at this stage. You know, some of the code dates back to the mid 80s, or a lot of the core functionality dates back to the 1990s. We've added on many new features since then, but over the course of time, we dedicate a small percentage of development time every release to making the program a little bit faster. And with version 8.6, it's about 5% faster than the previous version on average. So we take about 10 different analyses, usually random C, time domain dynamics, for different types of riser, be it top tension riser, steel catenary riser, flexibles or umbilicals, or something with pipe in pipe. And we run those every single time we do a new release. And then we take an average of what the speed is from version to version. And this occasion, it's about 5% faster than the previous version. That's not a huge amount, but we are incrementally making inroads each time in terms of speed. So version 8.1 was was a major speed increase on 7.9. I think about a 30% faster than it. In the meantime, we've added some more incremental improvements. So off the top of my head, I'd imagine that version 8.6 is probably about 50% faster than version 7.9, which was released about version 7.9 was released in, I would say, 2009, 2010. So in that space of time, we've had a 50% increase basically in speed. That's just to note that. So that encourages users as well to upgrade to the latest version, as well as the new features you get, and as well as the bug fixes. The software actually runs quicker with every new release reissue. Briefly, I want to move on to pipe-in-pipe models. This is quite a straightforward enhancement, really. When you model pipe-in-pipe in Flexcom, you have two options. You have standard connections and you have sliding connections, and this is what we term the two options. Standard connections would usually be used for, let's say, a top tension riser, where there is very little relative axial motion between the outer pipe and the inner tubing. And in that case, the user designates what nodes are connected to which, so which outer nodes are connected to which inner nodes, and they remain connected for the entire simulation. The other option is sliding, which is where the relative axial motion is very significant. So in that case, let's say for a J tube pull-in, where you're pulling a flexible through a J tube, the inner tube slides inside along the outer one quite a long distance. So at every solution step, Flexcom monitors the outer nodes against a group of inner nodes, and based on the relative axial location, it picks out the right connections automatically for you. So based on some feedback which I got from people who do a lot of drilling riser analysis or landing string analysis in particular, they wanted a kind of a hybrid of the two. So with the landing string analysis, you would have the outer riser, the marine riser, and you'd have the inner landing string. So in the initial static analysis, it's a little bit difficult to know what the optimum connections are, because the inner pipe tends to sit down inside the outer pipe quite a lot just initially. So there's a lot of realignment in the initial static analysis. But once the initial static is over and you go into dynamics, then there's very, very little change in the axial degree of freedom. So now with Flexcom, you can switch from sliding connections back to standard connections by just changing one keyword. And the keyword is just called star no pipe and pipe sliding. It's very simple, easy to use. The other thing I wanted to mention in terms of pipe and pipe is that the theory manual has been strengthened. So some feedback from users was that there just wasn't enough information available in terms of what's actually happening over time. What is the program doing when you press the run button? How does it determine what nodes are connected to what, and so on? So if you look at the pipe and pipe section of the manual now, there's quite a lot of stuff in there. So if I look at sort of contact modeling, it goes into detail in terms of how it determines what the primary and secondary nodes are, how it sets up local transformation matrices based on the instantaneous orientation of the outer element. Goes into the vector, how it sets up local axis systems, how the contact stiffness is applied in terms of that local axis system. A lot of stuff, and then how all that feeds into the global stiffness matrix and the right hand side vector. And then that's just in terms of contact modeling. Then there was issues in terms of hydrodynamic forces and how that's modeled. So you can basically browse through that information in pipe and pipe if you're interested in more detail or more transparency about what the program actually does when you model a pipe and pipe scenario with Flexcom. So it was maybe 2 or 3 pages. It's now maybe 12 or 14 different pages of information. Okay, that's the pipe and pipe section. Damper element. This is fairly straightforward. With damper elements in the previous version of Flexcom, the damping coefficient, which multiplied the velocity of the damper element by a certain coefficient to get a damper force, that was pretty much fixed. Now you can have a velocity dependent damping coefficient, which allows the damper element to respond dynamically to variations in the relative velocity of its end node. So you can customize it. It's not as restrictive as it was. It gives you much more control. Maybe stepping on, maybe looking at the next version of Flexcom or where we take it from here. My ideal would be to have a user-defined element, which is another step beyond what we've spoken about in terms of the user solver variables, but to actually be able to modify element properties dynamically as a function of time based on instantaneous solution conditions. But that's further down the line. But the advances we've made in this version are certainly a strong leap forward from prior versions of Flexcom. Damper element, okay. The additional outputs. This is, I think, is probably the last section I wanted to cover just before we finish. Go back to Flexcom itself here. Flexible riser. I turn on the element inspector. I turn on the model view. There we go. So I guess everybody is familiar with the element inspector feature. If you open up the model view and you open up the element inspector, then you can click on any element in the model. So you just press the control button and then the left hand mouse button, and that lets you select an element. So then you'll just select that white one there, and then it tells you the properties of it. So it tells you what the dimensions of the element are, what the diameters are, stiffnesses, etc. And it also tells you now some derived properties. So it tells you like weight in air and weight in water, excluding or including the internal fluid. Tells you what the displacement of it is, as well as internal fluid properties. So the element inspector, we've added some more information there just so you can click on any point in the model and bring up some local information just to double check your properties as a sanity check. It can be very useful for models which like a drilling riser, where it looks quite repetitive on screen. It's a bit different here because this model's got 5 different lines and they're all got different properties. But if you've got one long string and it looks the same, then it can be useful to click on a point on the model and see exactly what the properties are locally. The print keyword as well is just something I hope people are familiar with. The print keyword. Just bring up the help on that. So if you want some information about what's happening at solution at runtime, you can type in this print keyword into your model, and then it outputs more information to the output file than you'd normally get. Some of the stuff that's quite useful is maybe convected element axes. You can see what the local underformed or the instantaneous solution axis system for each element is. So if you've got a local Y in bending moment, you can easily see what the planes are in terms of their definition in space, which mightn't be immediately obvious if an element is undergoing significant rotation. If you've got fluid flow through the model, you can get a detailed output of centrifugal forces. Even for standard riser models, you can look at water particle hydrodynamics. So you can look at water particle velocities and accelerations at any point in the wave field, which again can be useful. So again, just something to bear in mind if you're not already familiar with it. Star print is quite useful. Okay, I think I'm almost there. Yeah, so a big thank you from everyone on the Flexcom development team. Got quite a nice group of users, even on this webinar, and globally quite a large user base for Flexcom. So thank you for listening today, and I hope you enjoy working with Flexcom 8.6.